Thank you for coming. So, yes, this is a session about certificates. So if you heard about certificates during this conference, especially like the speaker X talk about security. Thankfully, there is not so much overlap. We didn't know about that, but so yeah, my goal here is to really like to try to give you like basic information and a little bit more than basics, just so that you have the tools to understand what can go wrong, and you have enough information to know like what to ask for, and you know where the details, the little details that are important. So who am I? I'm Éric Falconnier. I'm the co-founder of Central. Central is a GitOps-oriented MDM tool with integration with OS Query Santa Monkey. On GitHub, I'm in P5, and in the community, I'm also in P5. So quick question. I mean, probably some of you here have already had like these things to set up or these problems. So who in the room had to set up like device identity with an Okta CA? Yeah? Not so many. Problems with ACOs, like problems with applications who didn't have access to the certificates, or no? And I don't know if any of you have experimented with managed apps on iOS with DDM configuration for identity? Also no. Okay. Okay, don't worry, we are going to start with the basics, so we're going to start really from the start. So even before the certificates, we are going to just a little few words about asymmetric cryptography. So it's a pair of mathematically related keys. There's a public key that you can share. It's encouraged to share. It's used for encryption and verification. It's absolutely not a secret. And there's a private key. It's used for decryption and signing that must be kept secret as much as possible. Sometimes we will see, like sometimes it's not possible, sadly, but it's like that. And so now let's have a look at how these keys are related when we say like it's a pair of keys. So without going too deep into the math, it's just the public key is the result of a one-way function that takes the private key as an input. And this is the basic of everything that is like in your credit cards, the TLS certificates, and everything. It's just this little thing, because one way means it's really, really, really extremely hard to go from the public key to the private key. And this is the only way it's working. And you have heard probably about quantum cryptography. So that's going to probably make some of these things easier to solve. Well, there are already algorithms that are quantum resistant. But yeah, so the algorithms that are used the most are modular exponentiation. So basically like it's a trick with prime numbers and modulo. And elliptic curve, I don't know if you've seen the slides from the IRU presentation yesterday, like one of them just sped through like some elliptic curves. It's really nice. The advantage with elliptic curve, it's like the keys for the same level of security, they are much smaller. And if you have like especially like one kind of key, like the P2056, they are supported directly by Secure Enclave. So it's definitely something to know and to think of. So we take these two keys, this pair of keys, they are related, but the key is not like an identity. So what we need is we need something to tie up the public key and not the private key with the attributes and some verified information about the holder of the key. It could be a device, it could be a person, it could be like in a smart card, but yeah. So it's really like, it's basically it. The issuer, the principal in the relationship that is going to validate the data and attach it to the public key is going to sign the whole thing. And this is it. This is just to prove that we attach some attributes to a public key. and that makes a certificate. So this is like a device certificate for MDM, for example. It's just like the interpretation in text of some of the fields. So we've got the public key, as I said. This is the thing that we want to attach information to. There's a subject, so it's already like the subject, so it's the bit of the identity. So here you can see like, put a secret, I replaced it because it's basically the enrollment ID. I put some extra fields in there. There's a serial number. Those fields are funny. I mean, you can get back to it afterwards because they are from the attestation. But we will get back to that. But it's basically like you put like some data. It's signed by an issuer. So that's the intermediate. There's a validity, of course. Here we have 1 year. And extensions that can indicate like how to use the key. So here it's a TLS web client because it's MTLS. It's like the authentication on the device. It's not the server certificate. And there's a signature. Makes it possible to make sure that the issuer actually signed this. Just to go back to the validity, I think I will talk again about that. It's a lot about like the kind of information you attach is important for validity. Like if you simply want to say, oh, this is the device and the key is in the secure enclave, and you just put like the serial number, and you made sure that the serial number is the serial number that is validated, you can have a very long validity because I mean, it's going to be really extremely hard to extract the key and do something else with it. If you attach some, if you convey more information, if you say, for example, I've validated the last OS version, and to issue the certificate, I validated that the last OS version was okay. And obviously, you cannot have a validity of 1 year. You have to reduce it. So it's probably not the best example, but think of it like the contract you have with the people who are going to consume your certificates, and you have to think about the validity of the information and how long you are okay to use it. So there's no wrong or bad. It's all about the information the certificate contains. So this is how you inspect a certificate. Don't worry, there's a QR code at the end. But it's basically like simple OpenSSL CLI tools. This is how you get the output. You can even filter it. Very simple. And they come in 2 forms. So if one form doesn't work, it's going to be the other one. So one form is just a raw bits, and the other form is base64 encoded with some headers. But if one doesn't work, it's usually the other one. So we've got the key. We've got the information attached to the key. And how do we verify everything? How does it make sense? The whole chain of trust, because it's what we have. How can it be verified? How can it be consumed? So we start with a root certificate. The root certificate is, again, a private key and a public key. So it's a public key with some information about the public key. But because it has to start somewhere, it has to be self-signed. You cannot, I mean, you have to start the chain somewhere. And those are the ones that are usually installed in the OS to establish the basic truth. So to establish the base of the chain of trust. And obviously, there are like really strict security requirements to be allowed to be into this chain of trust. Probably you have to have a public log of the certificates you sign. Everything has to be perfect. Because there had been like bad actors not doing really well with their private keys, signing bad certificates that were polluting all of that. And then you've got, and this key is offline usually. Could even be like in a hardware device somewhere in a safe with a signing ceremony with 2 people. It can be really interesting. Like you see these people rolling out the safe, and yeah, I don't know, pretty interesting. So the intermediate is live, and it's usually like if a root certificate has 10 years or 20 years validity, the intermediate is much shorter. And this is usually what is used like in a infrastructure to. It's usually what is at this level that the ACME and SCEP thing is happening. So the issuance of the NTT certificates. We're going to make a small detour because of the way the ASCII thing was generated. Little detour. Here we have like something else. We have a revocation list. So we've seen the validity of a certificate that is inside, but actually there's a way to invalidate a certificate by publishing it in publishing a serial of a certificate in certificate revocation list. But obviously, like the people who are consuming the certificate, they have to validate this. And the validity as well plays a role here, because if you have 1 year of validity, you have to keep a long track of revoked certificates. And if you have a short time validity, you might not even need a certificate revocation list. And then there's an identity certificate, the one I showed you before, the one for the device, and that's it. And then come Okta, verify, or the Wi-Fi endpoint, verifying the identity, so they validate the chain based on the root they trust. They might check the certificate revocation list, make sure that the device, the certificate is not on it. That's it. Okay, so really basic stuff. Really important principles. Obviously, the CA must never issue certificates to unknown entities. That would be defeating the purpose. The CA must validate the information. That's the most important thing. You don't put stuff in the certificate that you cannot verify. You don't trust anything. And I've introduced like sometimes they call it like the relaying authority or stuff like that. It depends. Like there are like ways of making it more complex, like in the roles, but basically it's the CA. The CA cannot trust the identity information provided by the clients. So there's a star here because obviously like there's a device attestation. But except from that, like anything coming from in the subject of a certificate sending request, anything coming like I want this in my certificate, you just ignore it, because you cannot trust that comes from the client. The private key would never be communicated, copy shared, and sometimes it's really sad because sometimes you have a P12, so the certificate, the private key protected by the password in the same payload, and you distribute it to everyone, and sometimes it's even the same to everyone. So this is really sad. But there are some products, they still work like that. Sometimes it's okay because it's a license key somehow, but that's really bad practice. And as an MDM vendor, we really don't like to have to touch private keys. We don't want them. We want to implement the protocols that don't need them. So we have the keys, the identity, the chain of trust, how they are consumed. And now we do like the certificate issuance protocols. So SCEP has a really bad rep. I kind of know why. I think some of it is a bit harsh because I don't know the history. Or maybe you had like some bad issues with it. Anyway, and Acme is it's a Cupertino gospel. It's going to solve everything. I mean, you've heard that in the talk. I think it's 95% true. And there's 5% where I don't agree. But it's my own opinion. But it's already really, really much better. So we start with SCEP. SCEP is old. So that's why you have to be careful. I mean, you respect the old people. I mean, just like, it comes from a different time. 2000. Wow, 26 years. So design around 2000 by VeriSign for Cisco. You understand, like even the companies are like, ooh, like old companies. Supported first by Windows 2000, you know, the one that worked. Dropped in 2010, dropped. Just like, no, move on, let's not use it anymore. I forgot what they replaced it with, like ESP or something like that. ESP, yeah. And then revived in 2015 thanks to Peter Gutmann. I don't know who it is. I mean, just a guy on the RFC, a request for comment. And it's really good because he noticed like it's a mess. Like everybody is using SCEP, and there's no standard, there's nothing. So let's organize all the stuff we know and try to make it so that it works. And there's a big, and with a big security thing about like the challenge, but we'll get to it. So that's it. Mostly, I think I simplified only the last bit. So somehow the device is woken up, says like, I need to do something and stuff like that. And the MDM realizes, oh, I have to distribute a SCEP payload. I'm talking like DDM or config profile. It's agnostic here. So there is a custom bit here that's probably not always there. Get a dynamic challenge. So you can have like a static challenge that is going to be the same for all the profiles. So it's a bit like, it's not so good because if you know it, you can get a certificate. And you can get a dynamic challenge, so it's more like a nonce. So every time there is a new payload to distribute for each device, the MDM is going to get one challenge, put it in a SCEP configuration, and it's going to send to the device. So there's always this little bit of interactions. It's always like this thing. And we can only do that on demand. I say we, MDM vendors. And then there's like the arcane stuff here, like always talk to the CA, ask like, what can you do? And then there's a public key cryptography again, because it was pre-TLS. So this whole thing was made to be on HTTP. It was meant to be like on clear channels. So they had to re-implement TLS. Basically, they had to re-implement who are you, I'm going to encrypt that for you, and everything. So it's a mess, but it's 2000. And then, so the device generates a key, builds a CSR with the information, sends the encrypted CSR, because no TLS. Well, you have TLS now, but yeah. And then the CA has to verify the CSR, ignore everything that is in it. I mean, some of them don't, but you have to ignore everything except the public key. This is where you can get some extra device info to know if a device is managed or not. This is not part of the protocol. It's more like, because you ignore everything that comes from the CSR, you have to make sure that the device is managed, and maybe you can attach some information with a dynamic challenge, saying like the dynamic challenge is maybe tied to a serial number, and you are going to template the serial number here. That would be great. That's why SCEP is not so bad if you do it correctly. You verify the info, ignore everything, send the certificates, done. Here it could be offline. Could be because it's meant for a human in the loop. Could be that you wait for someone to approve a certificate. It's an old protocol. Usually it's just like you send a certificate. So that's it. Just for a little joke, that's the dynamic, that's the way you get the dynamic challenge from Okta. So it's really Okta, pretending to be an Endes server, and pretending to be like really like the same color, the same design. So that's what Jamf is seeing when they're asking Okta for a dynamics thing. And we had to implement that as well to do the dynamic challenge with Okta. And the funny thing is that it's not quite Endes. It's not the same encoding. It's UTF-8. No, it's Windows something. And the regex has to be different because it's not the same challenge length. But yeah. So this is crazy. Huh? It's like, it's not an API. It's not JSON. It's a text thing that is Endes. And it's Okta. So the good, it solves the certificate issuance problem. It really works. It works like every day. The private key stays on the device, so it's really, really, really good. The bad, the challenge is the only thing protecting the exchange. I think so, yeah. And the dynamic challenges, they had some security, but they require custom acts, or they require to attach some information. They require some implementation on the CS side. It's not good, but it can get you there. And there's no standard to verify the subject information. Yeah, you just have to template it in. And the ugly stuff is really the implementation because it's pre-TLS, HTTPS everywhere was not there. So basically, you all put it like if it was like a GPG encrypted email. It's like the technology of the time. So we jumped from 2000 to 2013. And what happened in 2013? There was a first article in June 2013 about the NSA leaks, Edward Snowden, and all the things. And for the encryption of the whole internet, it's a massive, massive moment. There is really a before and after. So first article in The Guardian on the 6th of June. This is when Google realized that the NSA was basically tapping the fiber between their data centers. The internet needed to be completely encrypted because we were encrypting like only a bits of it. We were really naive. And then so an internet security research group developed ACME for Let's Encrypt. So Let's Encrypt a way to get certificates for everyone for free, stuff like that. And the first certificate, I mean, you can, I've put the link in the slide if you want, you can look at the first certificate. It was emitted in 2015. So, but ACME was more for server side of things. And so you are thinking like, how do you go from server side to device certificate? So in 2022, Brandon Weeks, working at Google, I think, proposed the device attestation extension. So, because there has been like a lot of progress on the client side, the TPMs, they have been well established. So it's a trusted platform module. It's a bit like the secure enclave, but for the non-Apple world. The Apple secure enclave, or the T1, the T2, the Apple managed device attestation, the kind of stuff. So it was possible for a device to prove its identity. So the whole thing that is missing in the SCEP thing. So it introduces two identifiers for ACME, because think of that. It's not a, ACME was DNS on IP, and it doesn't work for a device. So they had to introduce a new two new identifiers type for the device, and a new way to verify it, because ACME verifies the DNS record or verifies there is a file on the server, and here we just verify the attestation. It was first released with iOS 16, macOS 30. So it's a bit more arrows going everywhere, but it's not that. It's just a very verbose protocol. So you start a bit the same, and you realize like, oh, I cannot get rid of that. Not really. Well, you could a bit, like in the example that Tom presented, he put the serial number in the client identifier. But to be honest, like as a CA, we really like to have like a one-time thing, because we don't want every time like to work. So here you can have an optional thing where we give me a client identifier for this session. And then you send a directory, some information, a bit like SCEP. It's not so far. And then you do a discovery, because it's like, oh, well, how do you work CA? What do you like? Where are your endpoints? Stuff like that. And then you start the thing. I want to start the sequence. I want to create an account. It's just like, what? But yeah, like the same way you say, oh, I'm Eric at central.com. I want to issue a certificate for my cloud service. The same way the device has to pretend like to be someone and to want to issue a certificate for something. So every time they do an XMIS thing, they create an account on the CA. And every time it's a different account. That's a little thing that is annoying. And then they say, I want to order a new certificate with this hardware number. And then they say, the ACME certificate say, yeah, good, there's a challenge. Okay, give me the challenge, because it would be so easy to just answer with a challenge. And then that's where the attestation happens. So with a challenge, and with the identity of a secure enclave, they go to the Apple attestation servers, they have the data about the device, they answer with the attestation. And then they update the challenge, so we can prove the challenge was good, we can prove we own the identifier. Again, every Apple device on the planet can prove they are who they are, but they are not all managed by you. So you need an extra round, make sure that the device is managed by you. You can do that a little bit with the client identifier as well. And then you say, everything is good, and then it's the same thing. Generate the key pair, probably in a secure enclave, finalize the order, you verify the CSR, apply the user informed templates, because you ignore everything except the stuff that you can trust, meaning either coming from the MDM or from the device attestation. Then please give me the certificate, and you answer with the certificate. It's very, very, very verbose. It's like 3 times more HTTP requests. Device attestation is a certificate. So if you understand certificates, you understand the device attestation. There is an issuer, there is an intermediary, this is the servers we're talking about. There's a subject, and they are like all the good stuff that Tom was talking about, but here like it's more like directly in the certificate. So extensions, always attached to the public key, and then extensions. I've got everything you need. You need the bootloader, the version, the secure enclave OS version, the OS version, even the device ID for software updates, if it's full security, the serial number, the provisioning UDID, yeah, everything you need. And it's just a certificate. So it's very easy to verify, and it's very easy to get the information, and there's nothing else to learn. Just serialized differently, but it's the same thing. That's it. So the good. On the Apple platform, it's the only way to get hardware-bound private keys, so in the secure enclave. And again, make sure that you use the correct key type, because only the P256, I think, at least only the ECC are available in secure enclave. And with the device attestation, the CA can verify the identity of the device, which is really, really good. And the bad, it's still, we cannot remove the necessary communication between the CA and the MDM. Because they only can prove that the device is a genuine Apple device with the attestation. We don't know that it comes, but it's managed by us. So you can use the client identifier for that, and the CA has to understand it, or the CA has to do an API call to the MDM to ask, okay, I've received this serial number, is it managed by us? So there is always this communication, so that's why I'm saying like it's not solving all our issues. And the IGLI is like, well, it's an implementation details. As the customers, you don't have to worry for that, but it's extremely verbose. Like it's like 10 HTTP requests. And there is no way to say no to an order early enough. Like all this stuff that happens at the beginning, they are unauthenticated. Even the new account is unauthenticated. So everyone on earth can start the thing. And it's only like with a client ID that comes with an order that you can start saying like, no, it's not, no, I don't want you. So it's a bit hard on the implementation side. I mean, there are hacks, of course, but then you diverge from the thing. And so that's why we call like I wish there is something they would do. They would use like there's something in Acme to pre-configure the account, so we don't have to create the account for the device every time. It's a detail, but it's in the slides if we want to look at it. I wish they had that in the implementation. So we have a certificate. How do you make it available to the apps? Well, that's it. I mean, maybe like except some hacks or whatever, but it's basically like all or nothing. It's true or false. If it's Acme, SCEP, if it's DDM, if it's, well, at least on the Mac, it's true or false. And if someone has more information, I'm happy to evaluate that. So this is when it's not available for all apps, it's still available for a lot of apps, because otherwise the MDM will not work. And the Wi-Fi, so that's the thing, I think. So, and yeah, and of course, like we said, like, oh, great, we have Acme certificates, so we can do like great MTLS with Chrome, and we can do that, and everything is going to be great, and no, because it's not available. But there is hope. Maybe for macOS 27, we'll see. Well, anyway, on iOS, iPadOS, and visionOS, there's a managed app framework introduced last year at WWDC. And it's great because it's like an extension of, you know, like when you install an app, you can add like a little bit of config. Well, this is great because you can go really into details. You can add config, password, certificates, and identities, which is like basically certificates are root certificates, or without identity. Identity is the certificates that we were talking about like the whole session. And they can be SCEP identities, like identities. So this is probably the answer to the ACORS issue from Apple, saying like, with DDM, you can attach a certificate to some apps. And you can even reuse the same certificate with different apps. And you don't have to put it in the same config, like the old world. And so this is the ACORS solution. Yeah. So trust the math. And even like with the quantum cryptography and stuff like that, there are still possibilities. It's not broken. We just have to switch to something that is not really efficient at the moment, but is going to be efficient. By the way, like TLS 1.3, the handshake already between the browser and the servers is pretty much like, I think, it's solved now. It's post-quantum already. So even if someone would be recording all the traffic now, and having access to a very powerful computer in the future, they could not like decrypt it. So at least this part is already done. It's the encryption that is not like, yeah, it's different. Never trust the endpoints. So basically, like all the thing about like these extra loops, these extra API calls, these extra like things we have to put around SCEP on Acme to make it work and to make it secure, is because we cannot trust the endpoints except the attestations. But even the attestation is only like it's a healthy device. It doesn't tell you if it's managed by you or not. And yeah, if you get a P12, then you have to deal with it and just accept it. So that's it. Thank you. And of course, any questions or any corrections or anything, we have a microphone. And if you have a question, just wait for the microphone because it's better for the recording session. But it's up to you. And we can, of course, do it like in a non-recorded way later. Okay?
Good.
Thanks.